Log on, tune in, find out. Another good idea from Cambridge.
Well, so it's supposed to be switched on. Here we are, switched on. So I want to talk about recent developments in Vinogradov's mean value theorem. What I hope is at the end of this talk, you will, if you have not experienced Vinogradov's mean value theorem before, which is for many of you quite likely I would expect, then you should have some idea about how the classical version works, and also a reasonable idea about how the new developments might work. And for this reason, I'm not going to talk so much about the applications, which I could fill more than one lecture with, or the history. I'll give you an indication, but not too extensive a history. So what is Vinogradov's mean value theorem? So this is something which, for 75 years, it started about 1935, has been a central topic, in particular formerly with the Soviet school of analytic number theory. And I need a bit of notation to begin. So let me define an exponential sum, which is central to what goes on. So you should think of, so E of z, as usual, is e to the 2 pi I z. So this is an exponential sum over a polynomial of degree k, and these coefficients you should imagine as being real. And what we want to consider, this is the central object, is a certain mean value. So we're interested in the even moments of this object where I integrate over the unit cube. And to save time, I'm now just drawing a little circle here to indicate that I integrate over whatever is the obvious torus here. And from orthogonality, I mean, after all, the modulus of f of alpha squared is just f of alpha times f of minus alpha times its conjugate. I can interpret this as the number of solutions of a system of Diophantine equations. So this is a system of diagonal equations with degrees 1 up to k, and the variables here are all bounded between 1 and x, so we're counting solutions in a box. Why might this be useful? Well, if you're dealing in analytic number theory with any problem of some high degree k, you might be trying to approximate some function by Taylor's theorem, something like this, by a polynomial of degree k, then some exponential sum of shape similar to this will occur. So for example, if you're interested in the size of the Riemann zeta function close to the 1 line, then you're interested in summing n to a minus it. That's the same as an exponential sum with argument which is like log n over some interval. You can imagine that this sort of thing would be important. Of course, that's not the only application. There are applications involving Waring's problem and distribution mod 1 and so on, which I'll say a little about in a moment. But you should have an idea about what kind of bounds we would expect to obtain for this object. So as I said, this was a subject which started life in something like 1935. So this is the real Vinogradov, the one that counts. I am Vinogradov. The other one also counts, of course, but in a different area of analytic number theory. And this is something which was pursued extensively, so many people were involved in refining the estimate that I'll write down into something which is relatively simple to state. So here are a few names, Hua and Karatsuba, and there are other names as well. Linux was involved. So what kind of statement? So when S is at least k, there's an upper bound for this mean value which takes the shape, well, there's some number which depends only on S and k, and the interesting part is what happens when x is large as far as I'm concerned. there's an upper bound with exponent 2s minus 1/2 k times k plus 1. So this is the sum of the degrees of the equations which are involved in this mean value. And then there's some other thing, eta. And so the sort of the sum of knowledge up to the early 70s was that this difference between what we actually expect to have as an upper bound and what one can prove is bounded in a relatively simple form. So a half k squared times some power of 1 minus 1 over k. But the way to think about this power is that it's exponentially decaying as s increases, and the rate of decay is something like e to the minus s over k squared. So this is, yeah, you know the statement of what everybody knew up until about 20 or so years ago. This was the state of the art. I've downplayed the role of this constant here, this number depending on s and k. That's important for applications to the Riemann zeta function. I'm not going to talk about that at all. There are applications of this. So the key observation perhaps is that eta is small. So let's say something like 1 over k, let's make it rather small, when s is growing like a constant times k squared log k. And you can work out what kind of constant you want to use. So if I use 3k squared log k, then you can see that k squared e to the minus s over k squared is going to be smaller than about 1 over k. And small is a bit like epsilon. I mean, most things that you can do when you have this difference between expected and what you can prove being relatively small is almost as good as knowing that it's as small as expected. So, well, I mentioned in words some applications. It might be useful to say that because it kind of measures progress, if I just say a couple of words about the asymptotic formula in Waring's problem. So it's one of the obvious applications for this kind of thing. So here, what we're interested in doing is counting the number of representations of a large integer n as the sum of s k powers. And there's an expected shape for this asymptotic formula, which involves a classical gamma function. There's a product of local densities, which you could think of as being a constant. And then there's a power of n involved. You would imagine that when n is large, this number of representations should get larger. And what's known is that this asymptotic formula holds. Well, the classical state of the art was semi-classical, neoclassical maybe, was that this holds when s is at least 2 to the k plus 1. So that's something proved by Hua, which been proved on earlier work of Hardy and Littlewood. And people think about this problem a lot. So if you think about it a lot, then you care about saving 1. So that's something that Vaughan did, at least if k is at least 3. And if you're Heath Brown, then you do a bit better than that. But only if k is at least 6. And then Heath Brown gets very irritated because somebody saves for plus 1. So people think about this problem. And one of the big deals about Vinogradov's work was that, and maybe I'll state this in the form that Hua actually proved this in 1949, is that this asymptotic formula holds if the number of variables is not much bigger than 4 times k squared log k. So you can see, I mean, for large values of k, this definitely wins. And then there's a question about what large k should mean. Okay, so that's sort of a measure of progress, and I'll come back to this a little later, maybe other applications that you might care about. So you can try to understand the distribution modulo 1 of sequences. So I guess I learnt today that I should write this in some places. So that's a good thing that one can look at. You could be interested in Weyl inequalities, so maybe so that I don't have to write too much, maybe I'll think about an exponential sum like this, where I assume that I have a rational approximation to alpha of the shape A over Q, and then the upper bound that one would establish for this depends on the rational approximation Q in a convenient way. And again, it's a little bit like this asymptotic formula in Waring's problem. There's the estimate, which you're doubtless very familiar with, some of you at least, is something due to Weyl from 1916. The dependence here is exponentially decreasing with k, something like 2 to the 1 minus k. And then the Vinogradov work does better as soon as k is large. Okay, so something like 1 over 4k squared log k. Yep.
Conditions on S.
Yeah.
On the right-hand corner, and underneath Vinogradov 1949.
Yeah.
It's a different problem. I didn't count.
So it's the same. Once again, when established, you know the asymptotic formula holds if S is at least as big as this number instead of any of these numbers. So this, why isn't this obviously better than all of those? It's better when k is large because of little o1. Yeah. And you can be very precise, but this is asymptotically what happens when k is large. Okay. So those are some applications, and there's also been an application to some product theorems. That's Kroot and Hart recently, and there are even applications to moduli spaces, which is something very new, but probably no moduli space people are here. Too bad. Okay. So that was more or less the state of knowledge up until about 1990, and then I wrote a thesis which made an improvement in this. So basically, here's this bound that we have for eta here, and the short version of the thesis is essentially, or one of the results in the thesis, essentially that instead of e to the minus s over k squared, you can get a bound with e to the minus 2s over k squared, which, well, it hadn't been progress in a long, long time, so I could feel excited about this. So at the time I was very proud. So the asymptotic formula in Waring's problem then holds if s is at least 2 plus little o of 1k squared log k. And so, you have the number of variables. Very good. But in some sense, you can see that this fits into the same universe as the original Vinogradov work. And I should mention that Kevin Ford found a way of not just he used the same version of Vinogradov's mean value theorem, but more efficiently in this asymptotic formula in Waring's problem. And he was able to get to a result where you just have 1 plus little o of 1k squared log k. So that's not something which impacted Vinogradov's mean value theorem, but it was a more efficient use of that mean value theorem. Okay, excellent. So that's the world up to just a few months ago. And then what I want to talk about today is this theorem, which you can find on the archive now. I guess it appeared on the archive in 2011, but it was all done in 2010. And the theorem is that if k is at least 2, s is at least k times k plus 1, then then you have an upper bound in Vinogradov's mean value theorem where you get rid of this eta altogether. So eta is more or less 0 if you have k times k plus 1 variables. And maybe I should mention that the conjecture is that this object, well, but we should have the same sort of result without the epsilon when k is at least 3 and s is at least a half times k plus 1. So that's, we're within a factor 2 of the expected number of variables now. And maybe I should emphasize this is the first instance in any problem of large degree where we come within a constant factor of the expected number of variables in such a problem. So, so that's much nicer than my lousy thesis result. So I want to give, in this talk, I want to give an idea of how you prove this. And I'm not going to assume you know about Vinogradov's mean value theorem, so I think there's really a way to sketch this which makes sense. So can I ask, so if I use these extreme blackboards, is that kind of pointless for people, or is that's still visible?
Can you just, what does this imply as regards asymptotic?
Yeah, okay, so maybe, yeah, it's worth dwelling on my little moments of glory for a couple of moments. So the asymptotic formula in Waring's problem, whereas Ford had 1 plus little of 1 k squared log k, the simple, well, what you see on the web is a bound which is 2k squared plus 2k minus 3, when k is at least 2, which, well, it's better, you don't have to assume k is large, and also it's better anyway. And maybe the Weil exponent, it's also worth mentioning. So instead of 1 over 4k squared log k, or 2 to the 1 minus k, one gets a result with sigma of k equals 1 over 2k k minus 1. So again, it's quite elegant in some ways. Okay, I'm going to use these central blackboards for at least some of what comes next, because I want to make this visible. So I first want to explain how the classical version of Vinogradov's mean value theorem works. And I should mention right at the outset that the classical version in Vinogradov's language used the size of variables to impose a condition. And what you're about to see is the version that Linux invented, which makes use of conditions involving primes. So there's a distinction. If you look in Titchmarsh's book, for example, his account of Vinogradov's mean value theorem is all about the real place of infinity. And it looks a little different from what I'll explain, but it's really the same thing. If you're a number theorist, the place of infinity is pretty much the same as a local place. So I should emphasize this is really pretty much what Linux did in 1942. And the strategy is to bound j s plus k of x. So my notation, I had j s plus k comma k, and everything will be, k is kind of fixed, so I'm just going to ignore that issue. So in terms of js of x, and I'm going to tell you what this is all about presently. So this js plus k of x, remember it was a mean value, and I'll write it out here just so that you get to see it. So it's counting solutions of this system of equations, and all the variables are bounded between 1 and x. And the key observation that underlies Vinogradov's work and and Linux interpretation is that there's a translation, dilation, invariance at work here. So whenever I have a solution of the system of equations, then just as easily I have a corresponding solution where I sort of shift into an arithmetic progression. So in some sense, this arrow makes sense in both directions, only if q is not equal to 0. But if you think about this system of equations, which I've written down here, on the right-hand side, if I expand each of these terms using the binomial theorem, the top equation has degree k. You get similar equation, similar terms of degree k minus 1, k minus 2, and so on, and they get cancelled off by the underlying equations. So there is genuinely this translation, dilation, invariance that's at work. Okay, so that's an excellent observation. That should be useful. I'm going to define some notation which actually helps motivate, the notation helps motivate the argument that counts. So let me define an exponential sum which looks maybe a little strange to begin with, but so it's the same kind of exponential sum as I wrote down before, except that I'm going to restrict the variables to lie in an arithmetic progression, the arithmetic progression c modulo p to the c. And you should think here of p as being a prime, which I'm going to choose carefully. So think of p as being a prime between x to the theta and 2 times x to the theta, and we have to choose theta as before the end of the argument. So you should think, at least initially, of theta as being something like 1 over k. That's the classical choice. Okay, so that's just I mean, it looks very similar to the original exponential sum I wrote down. And maybe because it helps me with notation later on, maybe I should abbreviate this argument to, say, psi of x with parameter alpha. So what underlies the Vinogradov approach is that you would like to create a congruence condition amongst the variables. You can always create a congruence condition amongst variables of a Diophantine equation like this. The object is to make an efficient restriction. So the first observation is that by Holder's inequality, well, if I want to write down the original exponential sum f, and I mean, maybe confusingly, although it really doesn't appear later on, this was f of alpha x. So this original exponential sum, which is the sum over all, with no congruence restriction, this exponential sum, the sum of all residue classes, it's the same thing. So now, if I want to bound a power of this, I can use Holder's inequality so this is a sort of a trivial application of Holder's inequality. And I can use this to bound the mean value itself. So the mean value itself, remember, was the integral of the 2s moment of the original exponential sum. So this is js of x. So if I look at the 2s plus kth moment, I can replace 2s power of this exponential sum by this object, which I've carefully forced a lot of the congruence classes to be the same. So if I make use of the bound on little p, which I was assuming, I'll keep it explicit for the moment. So what do I have? I can write this as x to the 2s theta times a max over the possible residue classes of now the original exponential sum to the power 2k, and this 2s of these guys I'm replacing by this object. So I've got f1 of alpha and c here to the 2s. And this may look a bit obscure. What I've done here is I've taken c equal to be equal to 1 in this application. Okay, so that's just Hölder's inequality on 2s of these guys pushed inside the mean value here. We still haven't seen where this powerful congruence condition on the variables is going to come from, but inside this exponential sum, this mean value is counting solutions of an equation. And what equation is this? Well, this equation will exhibit the congruence condition which I'm after. So with 2k variables which look exactly the same as in the original problem, and then two s of these variables now lie in a congruence, the congruence class C modulo P. So if I fix a choice of C for now, so something like this. And I'll probably omit saying exactly where these variables lie, because it gets boring after a while, but just for transparency of bookkeeping for now, the variables x and y are bounded by x, and these u and v guys, well, because of the congruence condition, they go up to roughly x over p. Okay, so that was automatic from the application of Hölder's inequality, but it gave me this. All I've done is interpreted this mean value as in Diophantine form. And now you see I can apply this translation, dilation, invariance. So if I have a solution of this system, then I can translate backwards by C. Okay, that's legitimate, so that's the same system of equations. And now everything on this side is divisible by p to the j, so let's just make that more visible by doing that. And so now the original system of equations, where I forced a congruence condition mod p on 2s of the variables analytically, has now given me a new system of equations where I have congruence conditions. After all, this gives me a congruence condition, modulo p squared up to p to the k. So on the face of it, that's a much more powerful constraint than the original constraint which I'd imposed. From mod p, I've now got to mod p to the k in the uppermost equation. So, so our task now is to exploit this congruence condition so as to constrain the variables in a way which can be interpreted in a way which gives this recursion formula. So let's see what we've got from this process, just to emphasize, is that the sum from 1 to k of xi minus c to the j is congruent to the sum I equals 1 to k yi minus c to the j. We have all these, I should say what it's congruent, yeah, so mod p to the j runs from 1 up to k. Excellent. Okay, so now I have to, I'm going to lie at several points in this talk. So there's a big if here, which I can really convince you about this one, it's no problem. But if x1 up to x sub k are in distinct congruence classes mod p, and it's the distinctness which is important. So if that's the case, then the solutions of this system, this congruent system, they lift uniquely, or essentially uniquely, from solutions mod p to solutions mod p to the k. That's not quite true, I'll clarify that. So hence, we may suppose that x is congruent to y as vectors modulo p to the k if we inflate our estimates. Well, there's a compensating factor which I can explain. So the compensating factor is k factorial p to the half k times k minus 1. So let me say a few words about that. So you can imagine, I mean, I've got congruences modulo p, p squared, and so on. And I'd like to make a claim about solutions modulo p to the k. So if all of these powers p to the j were to be p to the k, then I'll be able to use a Hensel-Lemma argument for a system of equations to lift any one solution of this mod p to a solution mod p to the k. That would be correct. Even it would be correct and true. And even because these are a special system of equations, there's a nice way of doing this using Newton's formulae on sums of powers, roots of polynomials. So you don't even need Hensel to do this. Okay, now I said I was doing this modulo p to the k, and here I've got p to the j. So what I should do in order to make the conclusion here correct is to sort of upgrade the congruences mod p to p to the k. That costs me p to the k minus 1. And upgrade the congruence mod p squared to p to the k. So sort of p to the k minus 2 choices, and so on. So this factor here is just sort of a compensating factor to upgrade all my congruences modulo small powers of p to power p to the k. There's a little bit more involved, because how many solutions are there even mod p to this system? If I have one solution and everything is in distinct congruence classes, then I can permute the coordinates, and that's where the k factorial comes from. Okay, so that much is correct if you believe the if. Right, so you have to arrange that these variables are in distinct congruence classes to make this work, because if they're not, you have singular solutions and the lifting does not work so efficiently. Now it turns out that in the Linux work, there was a lot of work, a lot of trouble that was gone through in order to get quite such a smooth statement as the one I told you was the statement of Vinogradov's mean value theorem. And that work, in a sense, was about getting around this issue of having distinct congruence classes. But now we know it's very easy. So essentially what you can do is choose your prime in this argument in order that the bulk of the solutions really are in distinct congruence classes. And so if you average over a set of primes whose number is bounded in terms of k, and just k, then that's enough to ensure this condition. So I haven't really lied about this statement at all. You know, that's certainly very much under control. Okay, why is this useful? Okay, so we've already gotten to one punchline here, because remember that p to the k is larger than, well, if I make my initial choice theta equals 1 over k, then p to the k is larger than x to the 1 over k to the k, which is larger than the max of x, well, greater than or equal to the max of xi and yi. So this congruence condition actually forces x to be equal to y as integers. You know, I have a congruence whose modulus is larger than any of the integers involved, so that actually forces these variables to be the same. And that was really the objective of this classical version of Vinogradov's mean value theorem. So we started by imposing this congruence condition on the variables, mod p. It turned out that because the system was translation dilation invariant, you could force a congruence condition modulo p to the k. And if you choose your prime appropriately, larger than x to the 1 over k, but not much larger, then this forces a lot of the variables to be equal, sort of a diagonal structure. So, well, let's just see what this means for this mean value I1, which we were estimating. So if these variables are all equal to each other, xi minus c is equal to yi minus c for each of the i's, then this becomes 0. And so now we've got a similar system of equations to the original system. It's a sum over L of ul to the j minus bl to the j, but now just in s variables instead of s plus k. And if I keep track of everything I had here, so I had some factor, this depends on k, I don't really care about that, so I had a compensating factor p to the half k, k minus 1. That was from the congruences. Now, the set of variables x is equal to the k tuple y. So that's x to the k choices altogether. And now I have the number of solutions of this system of equations. And that's the same as counting the number of solutions in the original system, but with s variables. Except the range of the variables is only going up to x over p now. And really for boundary conditions, so I should really add a plus 1 here, but nobody cares about that. That's essentially irrelevant. So I bounded I1 in terms of js at a sort of a shortened range. And if I insert that information back into my earlier estimate for js plus k, now I've got this 2s theta here, sitting here, which is, maybe I should write this as x to the 1 over k, because theta was, remember, chosen to be 1 over k, to the 2s, times all of this stuff. So p, again, is x to the theta in size. So it's a half k, k minus 1. I've got my x to the k sitting there. And then this object, well, if I believe I already have a bound for this, the bound will look like x to the 1 minus theta to the 2s minus a half k, k plus 1, plus eta s, let's say. Eta s is whatever I could prove for the corresponding moment with s variables. Sorry, and theta is 1 over k. So now a bit of arithmetic takes place. If you're in a better position to do this arithmetic than I am, but I know what the answer is, so that's always useful. So that's the upper bound that you get by doing the quick bit of arithmetic there. So you can see that if I'm sort of hypothesizing a bound for this object, which is like x to the 2s minus a half k, k plus 1, plus eta s, k, s plus k, then implicitly this is giving a relationship on these permissible exponents, which has this 1 over k exponential decay. And if you do, there's one extra trick involved in doing this, but you can see basically that I'm getting exactly what I stated in the first version of Vinogradov's mean value theorem. So at least you've got the right impression there, right? So congruence classes, force congruence condition mod p on some of the variables, use translation dilation invariance to get congruences modulo p to the j, solve those congruences and iterate forces the variables to be the same, and you get this nice exponential decay. I'm not going to say anything in view of the time on what happened with what I proved in my thesis. So if you remember that essentially would put a 2 here instead of a 1. The idea, I can give you the one-line version, which maybe if you were locked in a room with a blackboard, you could work out what to do. So if x is congruent to y mod p to the k, and I chose theta to be smaller than 1 over k, I could try replacing x by y plus h times p to the k. That sort of exhibits the congruence condition. And then if I look at what happens when I substitute into this expression, I get differences of sort of the powers of y plus hp to the k and y, and the corresponding power of y. It's a bit like a Weyl difference operation. And you can recycle this via Holder's inequality and recover a system of equations which looks somewhat similar to the original system, but with these sort of efficiently Weyl differenced objects. And it turns out, if you're careful, you sort of recover a more efficient value of theta from this. So memory serves, the value of theta is roughly k over k squared plus eta s. That's the optimal choice of theta. Okay, so that's all excellent. So now, in the remaining time, I can give you a clue about what happens with the, or a strong clue about what happens with the more efficient version of this that's available now. So we're going to sort of take a somewhat orthogonal view of what went on in this earlier method. So in this method, as soon as we got this congruence condition, we tried to use this to force variables to match, to have this diagonal structure, which is very efficient. I mean, then you can kind of collapse the equations. So instead, what I want to do now is to use this congruence information as the starting point for an iteration very, very similar to what we had before. We paid a price in the earlier method to force some variables to be in the same congruence class mod p. And what we've done in this process is to force a lot of variables to be in the same congruence class mod p to the k. Well, that's a much stronger congruence condition, so let's use that and try to sort of repeat the process. Okay, so maybe I'll just record here. So far, what this method gave us was a bound which looks like this. Here, I should emphasize we're going to choose theta to be smaller than 1 over k, and in the first instance, you might choose to think that theta is going to be about 1 over k squared. And what do I want to say about I2? So I2 is now going to exhibit this congruence condition, which I had before. So I2 will be the number of solutions of well, we have a similar system of equations as we had before, which actually appear on the board just above my head. So what's going on with all of these variables? Well, the point is, the only important point is that WL and Z sub L we can suppose are in the congruence class C mod P, just by translating everything back again. And what we established from the previous argument was that x sub I could be forced to be congruent to y sub I mod P to the k for each I. So let me interpret that as the number of solutions of a Diophantine equation again. So this is equal to an integral. And now, well, let's pretend that this congruence class is eta mod P to the k and sum over all choices of eta. So now I have the exponential sum, which I introduced before. Everything is now congruent to eta mod P to the k. That's what this means. And so this is the mean value, which counts exactly the number of solutions here. Here are my 2s variables, all congruent to C mod P. That's what's going on with this exponential sum, and I already talked about this. Now, of course, it's inconvenient having lots of different classes here, so let's use Holder's inequality to simplify this somewhat. So I can force these all into the same congruence class. So there are p to the k choices here. If I write down p to the k minus 1 times the sum over eta of something, then this is certainly an upper bound for this. And then I can convert that sum over eta into a max if I like, which sort of simplifies things. Okay, so that's an upper bound, and if I get rid of this sum and put in a max, then this is really an upper bound that I have here. So it looks superficially like the integral I1, but notice that the arithmetic progressions to a high modulus are relatively few in number, to a low modulus a large in number, which is different from what goes on there. So if I really want to make this look rather similar to the integral I1, I should again use Holder's inequality. Maybe I'll use a new board for this. Yeah, I'm going to use this one. Yes, brilliant. Okay, so if I use Holder's inequality, I'm going to do this so far. Then what happens? So I use Holder again. So I2, I3, let's call this I3. This is supposed to extend over here. So I3, I can bound above by, now of course I did this, I prepared this all in advance, so I know exactly the right exponents to take. So one of the exponents is 1 minus k over s, and then there's a second mean value, which has f1 alpha c to the 2k times fk alpha eta to the 2s, the alpha, and that of course has to be to the power k over s. So that's really just an application of Holder's inequality. It really is visible. So this object, I should say, is, we already know about this. We already tackled this once in this lecture. This is bounded above by j s plus k of x over p. So because the variables are in a congruence class c mod p, then it reduces the length of the implicit sum here. But we know roughly what goes on there. This I4 we know less about, but it looks very much like this object here, doesn't it? Except that I've got a mod p condition here, and a mod p to the k condition here, where I had a mod p1 before. So you know exactly the right game to play at this point. So now, whenever I see a condition mod p, I should replace it by a condition mod p to the k. Blah, 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 blah. And now these guys are all constrained to go up to x minus c over p, and these guys x minus eta over p to the k. Everything is good. Okay. It's exactly the same system, it's just different congruence condition. Aha! So look at this. Yes, we have an excellent system of equations to consider here. Actually, I guess, did I? Well, it was basic. I've lied slightly, haven't I? So this should be eta, in fact. So I apologize about that. But so to be strictly honest, I should call this eta instead. But you get the idea. Aha! So if these are all in distinct congruence classes mod p, then this congruent system would lift uniquely from mod p, well, even mod p to the k, to mod p to the k squared. Well, there's a lie here already, because there's no way these can be distinct mod p, because they're all in the same congruence class modulo p. But it's possible that they're in distinct congruence classes modulo p squared. That's as distinct as they could be. Okay, since they're not in distinct congruence classes, but there's no longer this unique lifting, but you can compensate for the non-uniqueness. It's very explicit. So naively, in this kind of process, we would force these to be congruent to one another modulo p squared, p to the k squared. And what would this cost us? Well, it would be p to the k to the half k, k minus 1. That's not quite true anymore. Because of this non-distinctness, it costs me an extra p to the half k, k minus 1 to sort of compensate for that non-uniqueness. But that's all okay. Now, I mean, obviously, I've sort of iterated the process again, and I could try to do this all over again. There's a second big if here. This is a big if squared, right? Because I've already fixed my prime. I can't go fixing it all over again or choosing it all over again. But if you take on board what I said, you know, we could try abandoning the iteration at this point and just to see where we get to. So if I take theta to be 1 over k squared, that's a legitimate choice, then p to the k squared now is larger than, yes, x to the 1 over k squared, that's x to the theta to the power k squared, that's this power here. So again, we're forcing these variables to be equal to one another, but it's not transparent at this point what has happened with all of the steps which I've gone through in this process. So I can give you an indication of what happens, and sort of keep track of the exponents which are occurring. So somewhere or other. Right, so let's focus initially on I4, this mean value, which I wrote down. So just to indicate what happens. So I'll say a word about each of these bits right now. So this is the compensating factor from the congruence condition, exactly what I talked about a moment ago. Now the variables, if they are equal, remember they're in a congruence class modulo p. That's why this is just x over p to the k. Okay? And the remaining variables, when I've, unfortunately I deleted that part of the blackboard, remaining variables were in a congruence class modulo p to the k. And so the sort of the analog of js of x over p, which I had before, is now js of x over p to the k. And I can insert this in the overall estimate which I had, which is slightly horrifying, but in fact, there are ways which, once you decide that you're going to do a sort of a multi-step iteration, there are ways to understand what you expect here. So it's actually kind of an expected form in hindsight. So remember that at the top of the board there's this vector x to the 2s plus half k, k minus 1 theta times I2, and then we bounded I2 by a Holder's inequality in this way. So I2 is the number of solutions of an equation which is bounded by this stuff. So here I should write down js plus k of x to the 1 minus theta to the 1 minus k over s, and then there's an x, then there's this I4 stuff, so that's x to the k plus 1 theta to the half k, k minus 1 times x to the 1 minus theta to the k times js of x over p to the k, so that's x to the 1 minus k theta, and I pretend I know what this is. This is supposed to be 2s minus a half k, k plus 1 plus a to s. And all of that comes to the power k over s. I'm going to use this blackboard so I can stay in roughly the same position. So, so the point now is that we're going to hypothesize some bound for js plus k. And let's pretend that this has size which tells us about the exponent which we expect to put in a to s plus k. So to be careful, you should think of some infimum of some set of exponents and relate this to a corresponding upper bound for large x. You can take care of all this. It's just a bit of endgame stuff. So what happens then? So then this bound which we've got here, this is supposed to be js plus k of x, should be bounded above by this messy stuff. So I've got that initial factor. The next factor actually involves exactly the exponent which I'm trying to bound, but to a smaller power. And then I've got all this other stuff. And I'm not sure whether okay, so okay, so I mean that all disappears in a moment anyway, so I'm not so worried about it. Okay, so blah, brilliant. So this is the important part, and this over here. So maybe in the interest of time, I will not bore you by doing some arithmetic at pressure on the blackboard, but just comment that if you unravel all of this, obviously this is just a bit of manipulation at this point, you find that eta sub s plus k has to be bounded above by eta s plus k times, did I screw something up? I screwed something slightly up. Yeah, this is supposed to be 1 minus theta here. So eta s plus k times 1 minus theta times 1 minus k over s plus eta s 1 minus k theta k over s. And then there's if you do the arithmetic, there's this object on the end here. And I think, yeah, there's an extra k over s, which I should include here. Now remember, I was going to make the choice theta is 1 over k squared in this argument, so I get rid of this term anyway. And if I sort of play the game of taking this eta s plus k over the other side of the inequality, I find that I get a bound for eta s plus k in terms of eta s, which can be simplified. And the simplification already illustrates what is happening here. That term's disappeared already. Okay. So maybe you believe what I've written down here, and maybe in the heat of battle you've suffered fatigue and you've given up. But you can imagine that such a thing might be true. And the point now is that we've sort of diminished the naive estimate for this object by a factor of 1 plus s over k minus 1 theta. And theta was supposed to be 1 over k squared. So our upper bound for eta s plus k now looks like eta s 1 minus 1 over k, which is what I had in the classical version of Vinogradov's mean value theorem, divided by 1 plus s over k minus 1 times 1 over k squared. And if I want to approximate this just to get an idea of what's going on, that's roughly eta s times 1 minus s over k cubed, which is roughly speaking eta s e to the minus s over k cubed. And so if I iterate this repeatedly, I could imagine taking s to be a multiple of k. And you'll see, I've got this nice exponential form. I can sum that. So eta subscript rk, so a multiple of k, I've got some product of these things which appears now, which has quadratic growth. So this is looking a lot like k squared e to the minus a half s over k squared squared. And the classical version, which we had before, this looked a lot like e to the minus s over k squared. So what we've achieved by the second step of this process is to increase the exponential decay from sort of linear in s over k squared to quadratic in s over k squared. And you can see already or imagine that in the application to the asymptotic formula in Waring's problem, for example, whereas we had previously bounds which were of the shape k squared log k, now already this is giving something which is like k squared square root of log k. So already that's an improvement. So time is up, yes. I can open the floor for questions, but one question I want to be asked is, what about the big ifs? And I can also comment about, very loosely about what happens if you want to do more than one step of this iteration. But time is up, sorry, hand the floor over. Yeah.
Thank you very much.
Anybody have a question they want to ask?
What about the ifs?
What about the big ifs? That's an excellent question. Okay, so I mean, the first if, you could maybe believe that we could choose the prime in such a way that everything was relatively well behaved. So what happens with the second big if? So that big if was all to do with whether the variables xi are distinct mod p squared. So we know that they're all congruent to one thing mod p, one congruence class mod p. Well, let's suppose that these are not distinct mod p squared. Suppose that two of these variables are in the same congruence class mod p squared. Well, if you sort of followed the sense of what was going on in the talk, you would then say, well, okay, then we're happy because somehow that's a stronger congruence condition than we had before. But we should have realized that stronger congruence condition was available before I applied Holder's inequality in the top line of the blackboard bit. Because if I realize that at this point, it's already inefficient. So what I do is, what I suggest you do is that you prepare in advance. So in this integral I4, in the precursor to I4, you already think about what happens if you have this non-distinctness of congruence classes, so that you can exploit this extra information in the application of Holder's inequality there. So it requires, in a sense, preparing for this whole differencing process, use of congruences, a step ahead of when we actually apply them. You just need some forethought. And that's not quite the end of the story, because if you have a congruence condition which is not mod p, but mod p squared, or mod p cubed, or so on, maybe you impose an unexpectedly strong congruence condition on your variables, a really much stronger congruence condition than you expected. And in the part of the talk which I haven't said anything about, if you want to do a multiple iteration of this type, this kind of accelerates you towards the end game of the whole argument too quickly. You do so well that you sort of have to abort the iteration before you extract all the information that you want. And so you need to use some more pedestrian arguments to sort of give you suitable bounds in this very strong information situation, which you have to recycle into the iteration somehow. So there's this, an extra step there. It's an excellent question. Yeah. Well done.
Yeah. So you said that your result holds when s is bigger than k times k plus 1.
Yeah.
Why? What happens if it's just one less? Where does the thing break down?
Yeah. Okay. So.
So far I don't see it.
Yeah. In fact, you get just a hint from this part. So if I comment on if you apply a multiple iteration, so far we did one extra step compared to the classical version. if you apply somehow n steps, or maybe I'm wrong, maybe it's n minus 1, but n is big, then the kind of upper bound that in principle you would get from this situation looks very similar. Your choice of theta is necessarily smaller, so you get something like this, and I'm not missing anything. So this S over K came from the application of Holder's inequality. So I had to extract K variables, 2 K variables to play a congruence game with, and that's where this exponent came from. And as I iterate this whole process, the sort of power in this denominator gets bigger, as long as S is larger than K. But S really has to be bigger than K squared, because I still have to kill this somehow. So this is smaller than K squared, then I don't really win very much here. And remember that the moment that I'm actually estimating involves 2S plus 2K variables altogether. So that's where the sort of K times K plus 1 comes from. So somehow a factor K here comes from the fact that when I want to exploit the congruence information efficiently, I have to look at 2K variables altogether to impose this congruence condition. And another factor K comes from the fact that the congruence condition is going from P to P to the K to P to the K squared. So there's a sort of a growth in the power of P defining the congruences, and that growth rate is also like K. And I should say this is not quite the end of the story. I have some other results, but the picture is basically the right one to think about. And in fact, if you look at other translation dilation invariant systems to which these methods could be applied, there's a very similar picture. You can instantly predict what result you are going to, well, almost instantly predict what result you're going to be able to prove. It's the same kind of structure. Some number of variables to impose congruence conditions and the growth rate of the congruence condition. And I should say, I can't quite prove this. This business about distinctness mod powers of P causes significant complications, and so you have to sort of head for a slightly weaker version of this. But something still with the same asymptotic strength. Yeah, maybe it wasn't obvious. So if S is larger than K, just to spell it out, if S is larger than K squared, then this denominator is blowing up as n goes to infinity, and so this is smaller than any positive number. That's where epsilon appeared. Good.